Hello everyone. This is a short video going through some of the topics we've covered in this class. This serves as a supplemental guide as you prepare for exam one. First of all, what's the point of the slide deck? Why are you here? Why are you watching this? Uh, the whole purpose of the slide deck is to provide you with an overall picture of the various topics of the course covered so far. We've covered quite a number of topics here, so I wanted to make sure some of you understand how all of these different topics kind of fit in. I don't want you to get bogged down by some of the details and understand what are some of the main topics and how do they fit with the overall theme of the course.
I think the first simplest question, and we've been building a lot of models. We've been working with different data sets and creating models that accomplish different models that tries to predict different parameters. So I think the plainest question is, why do we even create these models in the first place? Depending on the situation, you may get different answers on what the point of models are. There are many ways you can kind of think about this. Some people say it's basically a way to trade offs, etc. There are a lot of different reasons why models are extremely useful. But I'll put it in our perspective for our class. Really, ultimately, it comes down to can we make models that have high predictive power? That's the main purpose in this class. And so for our class, a good model is one with high predictive ability. So it's able to tell us what's going to happen in the future based on what's happened in the past. So if you look at generally, a model is some kind of a representation of a real world system. So let's say in the real world, we have the spread of the turtle flu, some kind of a disease or a virus that's spreading and affecting human population. We can't really test out what's going to happen to the spread of that flu out in the real world as easily, because you can't just start changing things around as we want and see the effects. So instead, we try to model what would happen in the real world using a mathematical model. So we build a mathematical model of the real world system, okay? And then for our model, we want to know, for example, a certain output, like we want to predict the number of infections for 100,000 people for the infection rate. So in the real world, we can actually measure this in the real world. So we know we can get data from the real world, of this measurement, number of infections over 100,000 people or the infection rate. And then we can use our model then and figure out what parameters affect that output. So just as an example, let's say X1 is one of the parameters, percentage of people who are vaccinated to the virus. X2 could be the percentage of population with underlying chronic conditions. The argument is that these two parameters affect the number of infections for every 100,000 people. Okay? So these X1 variables are our inputs. And our output variable is a Y variable, or the dependent variable is the number of infections per 100,000 people. So our model tries to predict Y based on any value of X1 and X2. Okay? So the argument is that in the real world, if we know what X1 and X2 is in the real world, we can replicate this in the model and see what our model tells us. In the real world, then, if X1 were to give some value and X2 were to give some value, this would happen. This is what would happen in the real world. Okay? They're trying to predict what would happen in the real world. Okay, so that's really the point of making of models in our class. We want models with high predictive ability. And the next question is then, how do you actually create good models? So we know we need some input parameters X1 and X2 to produce the output of Y. We want models with high predictive power for Y, and then we have to decide which parameters X1, X2, X3, however many there are, which one of these variables are important in terms of determining Y, our output variable or the dependent variable. So we use existing data to create these models. There's only two types of models we've actually covered so far, which is a linear regression or the discrete regression model. And they work very similarly. It really comes down to the nature of the output variable you're trying to predict. If you're trying to predict the number of infections for 100,000 people, you would use a linear regression because the output would be some linear variable. So the value will range from anywhere from 0 to 100,000 supposedly, but it could be, it could range from, it could be decimal values, it could be any range of values, right? But if the y value is actually whether or not a person is infected, then that's a logistic regression model, okay? Because the variable we're trying to predict is a binary variable. It's a yes or no, 1 or 0, or true or false. Therefore, so the question of whether you use a linear logistic regression model depends on the nature of that dependent variable. If it's some kind of a numeric variable, then it's a linear regression. If it's a binary variable, then it's a logistic regression. Okay, so both of these models, whether linear or logistic, they use independent variables x1, x2, x3, etc. to predict a dependent variable y. So it's going to use a set of independent variables to predict y. We want these x variables to be not collinear, so we want them to be independent. Okay, so we want to avoid collinearity. Okay, we want these nice, clean variables that do not have any relation among themselves. Okay, so the way we create good models, once we decided whether we're building a linear regression or logistic regression model, is very, very similar. So we're going to use either forward selection or backward selection. So the first two rows of those two tables of the table shows you whether you're building a linear regression model or logistic regression model. You can use the forward selection or the backward selection method. The forward selection method means you add one variable at a time to your model until you're satisfied. Okay, so ultimately the type of models that we want is what's called a parsimonious model. That means the fewest number of variables and still has a high performance. So in forward selection, if you're doing linear regression, you're going to add one variable at a time until, for example, your adjusted R-square value no longer increases if you're using adjusted R-square as a parameter. Same idea with logistic regression, but adjusted R-square doesn't exist in a logistic regression model. So we use what's called an AIC parameter. It's analogous to adjusted R-square, but in this case, we want the lowest AIC, not the highest AIC. For adjusted R-square, we want the highest adjusted R-square. That's per iteration, right? So you start with one variable models, you pick the one with the highest adjusted R-square, move on to two variable models, pick the highest adjusted R-square, and then to the three variable models, pick the highest adjusted R-square, etc. Instead of using adjusted R-square or AIC, we could also use a p-value criteria. This one's a lot quicker or easier to implement in a sense that all you have to look at is a p-value, and if it's over 5%, and if anything over 5%, out of the ones that are over 5%, you remove. If you're doing if you're doing backward selection, you're removing the variable with the highest p-value. Okay, so backward selection is the complete opposite of forward selection, where you start with the full model and you start removing one variable at a time until you see no more improvement. Okay, so then it's the same way for linear regression or logistic regression. So let's say I'm using p-value now for backward selection. Then I'm going to remove one variable at a time until all of my variables are at a significant p-value, so under 5%. Now, at an iteration, if I see multiple variables that are above 5%, I'm going to pick the one with the highest p-value and remove that variable. Okay, and the method works exactly the same way, whether it's linear regression or logistic regression.
The Python call to build these models is the OLS function and the logit function. So you're going to use those functions to create either the linear or logistic regression model. So there are other ways to do it, but these are the calls the function that we've been using in our sessions. To be clear here, again, even if we were to implement backward elimination or forward selection and come up with a parsimonious model, there's no guarantee that our model will perform really well. There's just no guarantees. Just like in life, there's no guarantees, right? So this is our best guess, and hopefully our model performs well. So then, how do you actually measure our model performance?
We need to measure whether our model actually performs well on the testing set. So this is the data that was not used to build a model. We use a training set to build a model. So this is a completely new data set that model has never seen. So if our model does really well in the testing set, we know that our model generalizes very well, and it could be very effective in some of these newer cases. So if you're using linear regression, what we typically use,
we typically use the RMSC for linear regression as a performance measure criteria, or for logistic regression, we can use the area under a curve, AUC, but oftentimes we evaluate using the confusion matrix. And if we, based on our discussion on logistic regression, this idea of performance measure, there's a trade-off, right? Do you want to basically predict the truth correctly, or do you want to predict the false correctly? So it's a little bit more nuanced than a straightforward, performance measure like the RMSC. So we have to be aware of, when you're trying to compare logistic regression against another model. AUC is probably the most easiest way to kind of think about it, but the confusion matrix is another thing we have to think about. The Python call for making a prediction is your model, name of your model, dot predict, and inside the parentheses, if you leave it blank, it's going to make a prediction on the data that you use to build a model. But if you're going to predict on a testing set or another data set, then you would have to put in a data frame in there. And I just called it test_df here. Sometimes we would do pd.dataframe, actually write out the call or write out the statement that creates a data frame. But inside that parentheses and then predict, you would have to put in an appropriate data frame for Python to make a prediction on a new data set. If you leave it blank again, it'll still make a prediction, but on the data that you use to build the model. Let's move forward and talk a little bit more further about logistic regression.
If you want to measure effectiveness of the logistic regression model, we really need to calculate the sensitivity, specificity, and the accuracy. There are other parameters that we are interested in, but we haven't covered it for the course yet, or I haven't talked about it in detail. So for our discussion for now, we're just strictly going to look at sensitivity, specificity, and accuracy. Since the logistic regression models produce a probability value, when you actually run the model, the output you get from the model is not a 0 or 1, but a probability value. So we need to basically classify or basically map those values into a 0 or 1 or false or true or no or yes. So it depends on the threshold value. So our logistic regression model, we give it some inputs, and the outputs are going to be predicted values. Those values, again, are not yes or no or 0 or 1. They're going to be a value from 0 or 1. We're going to use what's called a threshold value. It's going to be 0.5 by default, but we could change this. And then we use that threshold value to create a confusion matrix. So if our output sample is, for example, greater than t, assuming that our threshold value is t, if our model outputs for a given sample, if our model outputs a value greater than t, then my model predicts 1 for that sample, or a true or yes. If the value is under t, less than t, then my model predicts 0 or false or no. Yeah. Taking those results, then I can create a confusion matrix. So let's say this is an example with t equals 0.5. This lists out all of the outcomes. So the value in the lower right-hand corner are the values where my model predicted true and it was actually true. The 52 is number of cases where my model predicted true and it was actually true. Okay. This 80 here, this is a value where my model predicted 0 or no. In this case, no means deny, yes means approve. This is the case. The 80 is the number of cases that my model predicted 0, and it was actually 0 in the real data. Okay? So if I were to change the threshold value to 0.2, though, for the same set of outputs from my model, I'll get a different confusion matrix because again, the threshold changed. So the way you map those probability values into an actual prediction of 0 or 1 changes. So in this case, with the same exact output from my model, there are 70 cases in which my model said 1 and the data actually showed 1. There were 21 cases where my model predicted 0 and the data actually shows also 0 as well. Okay. The sensitivity for my when t was 0.5 is the number of times my model predicted correctly over the total number of cases, or true cases, or one case. For the same model output with a different threshold value, my sensitivity actually changes. It goes up, and that kind of makes sense because the threshold value got smaller. That means my model is predicting 1 more frequently, and so it's going to catch a lot of those true cases more often. So my sensitivity goes up. But the specificity in my original case was higher, so it's 80 divided by 80 plus 13, so all of the actual 0 cases. But when the threshold goes down, my model is worse at this parameter because it's not picking up the 0 cases as well. So that's, again, the inherent trade-off that's shown by the ROC curve. The overall accuracy of these two models also change, again, because of the way I chose my threshold value. Okay, so the way you assess performance between a linear regression and a logistic regression model are different. So you got to be able to understand why they're different. And hopefully this gives you a good overall picture on all of the topics that we've covered so far relate to one another. Okay, thanks for watching. Bye.